Hello everyone, welcome to the SIMS and EPMA. You may be wondering what is the full form of these. Definitely we will come to know very soon. So basically what we are going to do, last class we saw very important technique, radiotracer diffusion, utilized to measure the diffusion coefficients, and we saw the ranges and so on, advantages, limitation, what it can do, and what is the drawback. So today we are going to see two more direct methods of measuring the diffusion coefficients. One is known as SIMS, which stands for secondary ion mass spectrometry, and other is EPMA, which is electron probe microanalysis. In some references, you will also see it is written as EMPA, so that is electron microprobe analysis. So these are the keywords, and we will be covering the basics of SIMS and EPMA in this lecture. Before we start the secondary ion mass spectrometry, let me just briefly tell you what is the sputtering process. So I am sure you might have heard this term called sputtering. So sputtering is basically you have a primary primary ion beam which impinges on the surface, and it deaccelerates during the impact with the target material. So if this is your target material and there is a primary ion beam of a certain energy, it will basically impinge with target and deaccelerate by partitioning its kinetic energies through a series of collision. So you can imagine that your target material is having a lot of atoms, a huge amount of atoms, and this ion beam basically interacts with these atoms, and it loses its energy, it deaccelerates during this process. And how much it can penetrate into the material, it will depend upon the energy, the type of the projectile, the target atoms, the atomic masses, and the angle of incidence also. Then each primary ion can initiate basically a collision cascade. That means one interacts with another, another interacts with the second atom, and so on. So basically it initiates a collision cascade of the displaced atoms, and the momentum vectors of these displaced atoms can be in several directions. So if the energy of these collision energies and the phonon energies of the target atom exceeds a certain threshold energy, then the atom is ejected out of the surface, and the rest of the energy is basically dissipated into the atomic mixing and heating of the target. So what we want to say is that when a primary ion beam interacts with the target or is incident on a target, there are certain atoms which can be displaced from the, or which can be ejected out of the surface. So this yield of atomic and molecular species coming out of a surface, it strongly depends upon the target atoms, on the primary ions and their energy. It is intuitively easy to understand that if you have a beam of very low energy impinging your target, then there will be very few atoms sputtering out, or even sometimes it may be none. But if you have a very high energy of ion beam, again it will eject out more atoms from the surface. So the yield typically varies between 0.1 to 10 atoms per primary ion. And if one uses the reactive primary ions like oxygen or alkali metals, then the yield is enhanced because of the interaction of the chemically reactive species with the sputtered species. So now let me tell you what is this secondary ion mass spectrometry. Let us basically look at the schematic of the instrument. So basically you have an ion source, and if this ion source or the primary ions impinges on the sample, then the secondary ions are generated. And these secondary ions, then their energy is analyzed as well as their mass is analyzed using an appropriate detector. So what you get is basically a mass spectrum, and you also get an imaging. Basically, you also get images. So these secondary ion mass spectrometry utilizes these secondary ions, and it basically resolves the mass of each ion using an appropriate detector. And when this primary ion beam is impinging on a sample, a certain amount of area is scanned by the ion beam, and when it goes more and more into depth, it creates what is called as a crater. So, for example, if ion beam has removed one layer, two layers, it may remove 100 layers. So, depending upon the number of layers that are removed from the target material, a crater is created. Okay. And similarly, you can basically choose an area, several areas of interest where your primary ion beam hits the target, and there are different craters that are created. So, as I said, the layers of atoms are sputtered off from the surface of a solid, and the resulting ions can be analyzed in a mass spectrometer. And for the diffusion measurements specifically, most common detectors that are used are known as time of flight detectors. We'll see more about them very shortly. These time of flight detectors have very high lateral resolution of 60 nanometers and high depth resolution of 1 nanometers. That means very thin layers can be analyzed from this. So, therefore, you will see, if you remember the previous lecture, we showed a figure, the range of diffusivity each technique can measure. So, in that SIMS is suitable for measuring the lower diffusion coefficients. So, the mass spectrum is scanned, and for the different tracers and the host atoms, the spectra can be recorded. And conventional beams, as I said, a crater is dug by the ion beam, and an aperture prevents ions from the crater edges from reaching the spectrometer. So, basically, the diffusion profile is constructed from the plots of instantaneous tracer to host atom ratio versus sputtering time. So, initially what you get is the source versus the instantaneous tracer versus the host atom ratio, and then you plot it with respect to the sputtering time. Then if you know already how much is the crater depth. So, the depth of the crater is measured by a profilometer. So, basically you know the intensity versus time, and that you can, if you know the distance, assuming a constant removal rate, you can basically convert it into a distance plot. The large changes of chemical composition can invalidate this assumption in certain cases. So, the diffusion analysis by SIMS, it also depends on the accuracy of measuring the depth of the eroded crater and the resolution of the detected concentration profile. So, the depth of the crater has to be also measured properly. So, as I said, that the SIMS enables the measurement of very small diffusion coefficients which are not attainable with mechanical sectioning techniques. SIMS also offers a very good depth resolution, and high sensitivity of mass spectrometry allows the resolution of these profiles of solutes in the 10 nanometer range and at the ppm level. So, SIMS basically for the diffusion measurements have been applied for the foreign atom diffusion. So, self diffusion, although people have tried, but it is mostly applied for the foreign atom diffusion, and it also permits the separation of stable isotopes of the same element. So, in certain cases, definitely, for example, nickel 64 is an isotope which is definitely used to study the self diffusion in nickel and nickel containing alloys, but more commonly SIMS is used for the foreign atom diffusion. So, a couple of examples of the primary ion sources I wanted to show you. So, there are two major types of sources that are used. One is called as a duoplasmatron. The schematic is given here. So, basically where there is a gas which is supplied, and through an electromagnetic setup, this gas is heated and ionized, and a plasma is generated. and then by the application of the voltage through the extraction electrodes, this plasma is converted to ion beam. And this ion beam basically can carry, for example, different types of ions, which can be also filtered out later depending upon which ion we want to use. So, this is what is explained here, that oxygen is commonly used because it enhances the yield of electropositive elements such as aluminum, silicon, and rare earth elements. And it may be used to extract either O minus, O2 minus, or O2 plus depending upon the electrical polarity selected by the operator. And O minus is the abundant species in the negative mode, and O2 plus is abundant in the positive mode. When insulating samples are being analyzed, O minus has a certain advantage which prevents the charge buildup on the sample surface. So, many ion species can be generated within the duoplasmatron, and as I said, it is left to the primary beam mass filter to select the desired ion beam. So, usually duoplasmatron is very effective, and it is quite commonly used in several of the SIMS equipment. Another common ion source is the cesium ion source, where a cesium containing compound, for example, a cesium chromate is heated and the electrons are collected, or the ions are hit the tungsten heated tungsten plate, and then these ions are generated, and an ion beam is collected, which then can be utilized for the further sources. So, as I said here, that CS ion beams, they are used to enhance the yield of electronegative elements such as carbon, oxygen, sulfur, etc. within the target, and the CS gun can only operate in the positive mode. So, in general, the CS beams are smaller than those generated by duoplasmatron, and the sputter material yield is more because of their greater mass. However, the CS guns, the cesium gun, is expensive to operate and is only routinely used for oxygen, sulfur, or carbon isotopic analysis. When insulators are analyzed, some method of neutralizing the positive charge buildup created by CS plus beam is required. So, as I said in the previous slide, usually for the insulating material, O minus ions are preferred. So, this is done. I already told you that by heating the solid cesium compound, and these vapors travels along the drift tube. This is the drift tube, and strikes the tungsten plate where it is thermally ionized. Now, let me also tell you a little more about the time of flight detectors. So, this is the schematic of time of flight detectors. These detectors are based on the fact that ions with the same energy but different masses travel with different velocity. So, you can see here, for example, the energy of the ions is same because it depends upon the voltage that is applied and their charge. So, for a particular material, the charge of the ions and the voltage applied will remain the same. So, the kinetic energy is also equivalent to half mv square. So, therefore, the time that is taken for the ions to reach the detector will depend upon the mass. So, higher the mass, more is the time that is required. So, higher the mass, lower is the velocity, and therefore, more is the time that is required to reach the detector. So, they are these ions are accelerated by this electrostatic field to a common energy, and they follow a drift path to the detector, and the lighter ones arrive before the heavier ones, and the mass spectrum is recorded. So, it enables the analysis of an unlimited mass range with high sensitivity, and simultaneous detection of all the secondary ions can be done by the mass spectrometer. This is actually very sensitive. You can detect very closely, very close isotopes. So, that means isotopes which have a very close difference in their atomic masses can also be detected by these detectors. So this is an example of a SIMS profile which is taken from this particular paper, where the lithium fraction versus depth is measured for the crystalline samples. So you can see that it follows a Gaussian behavior. This was the profile obtained for the as deposited after the diffusion at 16 minutes for 16 minutes at 150 degree centigrade. The profile changes like this. What you should notice actually is the depth. So when we saw the tracer diffusion in the last class, you saw that the depths, even with the ion beam sputtering, were close to 6 microns and so on. And if you use a mechanical sectioning, it is much more suitable for a higher depth of diffusion. Whereas with SIMS, you can really go up to the nanometer level. Although the disadvantage would be that if your actual diffusion depth is in microns, then SIMS may not be useful, because then the sputtering time will be too huge and it will just not be efficient. So therefore, SIMS is more suitable for measuring the lower diffusion coefficients. So let me summarize here some of the advantages and the limitations of SIMS. So one advantage is that it has a higher depth and lateral resolution. That means you can have nanometer layers analyzed using SIMS, and the lateral resolution also you can choose small areas to analyze the diffusion behavior. And then the high sensitivity also allows the detection of very low concentration levels. So here also you can deposit the tracer atoms in the lower quantities. Remember, when I am using the word tracer in the context of SIM, it is not a radioactive isotope. See, tracer, as the word suggests, it is something which with which you trace the atom. So basically, it is the atom that you trace. It is radioactive when you are using the radiotracer analysis, but for example, in SIMS, when you are using, you can use a stable isotope which is non-radioactive, and you can deposit it and let it diffuse and measure the profile. It is very useful for the low diffusivity measurement, and the post diffusion annealing characterization allows to develop the correlation with microstructure. So this is another very powerful advantage with SIMS, which is not available with the radiotracer technique. For example, you can suppose if you are measuring grain boundary diffusion, and there are different types of grain boundaries in your material, then you can actually mark the grain boundary through some indentations and so on, then perform the diffusion experiments, and then also after the diffusion experiment, you can again characterize the sample and try to locate the exact same boundary and see what has changed after the diffusion has happened. So such kind of a correlation with the microstructure of the diffusion process is possible with SIMS, which is not available with the radiotracer technique, because in radiotracer technique, once the radioactive isotope is deposited on a sample, no further characterization can be done, because it is contaminated by radioactive elements. Looking at the limitations of SIMS, it is suitable only for the low penetration depth measurements, particularly for impurity diffusion. If your diffusion depths are higher, then it will need a very long time for sputtering. That is very, very impractical. It's a relatively localized technique, as you saw that the crater depth, for example, can be in the range of 100 microns by 100 microns, or maximum 300 microns by 300 microns. So not the depth, it is the area that can be scanned by the beam. So if you want to basically have a large sample analyzed for diffusion, then you need several such craters to be made, and then you have to take some kind of average. If you don't choose several craters, then you will not be getting statistically reliable data. So in that context, it is a relatively localized technique, and the initial equipment cost and is very high, and even though the time of flight detectors are very suitable for measuring the diffusion profiles, it still has a limited applicability for the diffusion. You can also read about, because this is a diffusion related course, so only I have talked about the TOF detectors, but there are other detectors that can also be attached to SIMS, which are used for different types of applications. Typically, you will see that SIMS also find a lot of usage in geology, in analysis of minerals and so on. So, you can read further on that if you are interested. Then now let us talk about the another technique, which is electron probe microanalysis. So basically, the ability to perform a chemical analysis, it is also the result of a simple and unique relationship between the wavelength of the characteristic X-rays emitted from an element and its atomic number. So, how much is the wavelength of X-rays depends on the atomic number Z, which is a rather simple relation that the lambda is root lambda is inversely proportional to the Z. So, this that means if higher is the atomic number, lower is the wavelength of the X-ray, the characteristic X-ray that are emitted. And you already know about the process of the ejection of X-rays. So, basically, if incident electron has a sufficient energy, it can eject an orbital electron out. And this electron, when it is knocked out, an outer shell electron can fill its space, and as a result of this, a photon is generated. And if this resulting photon basically comes out of the atomic area, then this is basically an X-ray photon. Whereas if this can knock out another electron, this is called as a Auger electron. So basically, you can have the generation of X-rays, as well as you can have the generation of an Auger electron. And actually, both of them can be used for analysis of the diffusion measurements actually. So basically, they can be used to characterize. In this case, today we are talking about the X-ray photon that is used for EPMA, but you also have something called an Auger electron spectroscopy, where these Auger electrons are used. So, this is the schematic of EPMA optics, which is very similar to what you have for SEM. So, basically, you have an electron source which gives rise to an electron beam. This sources also can be dependent, their energy of the beam depends upon the type of sources that are used. You have lab-6, you have tungsten filament and field emission guns and so on. And this beam basically it strikes your sample, it passes through different set of electromagnetic lens, condenser lens, objective lens and so on. And once it hits your sample, the X-rays are generated, and these X-rays, if they can be detected, usually in SEM you will find that EDX detector. In EPMA you have basically the wavelength detector. So, this EDX or EDS is the energy dispersive spectroscopy, whereas WDS is the wavelength dispersive spectroscopy. So, here in EDS you are analyzing the energy of the X-rays that are coming out, and here you are analyzing the wavelength of the X-rays coming out. Nowadays in EPMA you have both WDS and EDS detectors. Earlier EPMAs usually used to have the WDS detectors only. So, you have the reverse also option in SEMs also predominantly, although EDS detectors are used, but some SEMs come with the possibility of attaching a WDS as well. So, this is an example of a typical profile that is obtained from EPMA. So, it is obtained by examining on a polished cross section of a diffusion sample the intensity of the characteristic radiation in the diffusion process. So, here you can see, for example, this is a silver aluminum diffusion couple, and here are the different zones in the interdiffusion that are formed. So, you can see this phase phi here, the delta, the mu phase, and this is the line along which the EPMA scan has been taken. So you can see here, this is the composition of the different phases that are obtained. And as we read, or as we saw several examples in the week where we did the interdiffusion lectures, so you can see that, for example, this phi phase has a constant composition, so which indicates to us that phi is a intermediate phase with a narrow composition range. Okay, so like this, here you have pure aluminum, here you have pure silver. So the detection limit in terms of atomic fractions is about 10 power minus 3 to 10 power minus 4. Depending upon the atomic number, it decreases with decreasing atomic number. Very light elements such as carbon or nitrogen are difficult to study. It's not impossible, but they are difficult to study because the fluorescence yield is low. So one major thing is that the diameter of the electron beam is actually about 1 micrometer. So the spatial resolution is rather poor in EPMA when you compare with some other techniques like SIMS and so on. So therefore, it is suitable to measure larger diffusion coefficient, something in excess of d greater than 10 power minus 15 or minus 16 also is possible sometimes, but typically greater than that only you can measure reliably using the technique of EPMA. Otherwise, the spatial resolution, because it is not so great, so you will have overlapping points. So therefore, because of the detection limit, it is mostly used for the interdiffusion and the multiphase diffusion studies. So a little bit more in the next few slides, we'll talk about this WDS, which is the wavelength dispersive spectroscopy. Basically, it relies, the schematic of WDS is something like this. So remember, WDS stands for wavelength dispersive spectroscopy. So here the electron beam falls onto the sample and the X-rays are generated. These X-rays basically fall onto an analyzing crystal. These crystals are usually single crystals which have specific planes. The orientations are taken care of, and when the X-rays and this crystal, when X-rays fall on the Bragg angle, when the Bragg law is satisfied, then the diffraction happens and the diffracted beam is detected here in the detector. So this is how the X-rays are detected, and the geometry is maintained such that the sample, the detector and the crystal, they follow on the circumference of a circle, which is known as the Rollin circle. So when the electron beam impinges the sample, the X-rays are emitted at a particular angle, and this angle that it makes with the surface is known as the takeoff angle. And this length of X-ray absorption is basically k times the cosec phi, and typically phi is about 40 degrees when it comes to the EPMA detection. And so in the setup of EPMA, usually the sample is fixed. It is the analyzing crystal and the detector which simultaneously move. So you can see here, this 1, 2, 3 indicates the direction of the movement of analyzing crystal and the corresponding movement of the detector, such that it is ensured that at any time all the three fall on the same Rollin circle. And you see here the way this is adjusted is such that the X-ray takeoff angle does not change. So this is the direction of the crystal movement, and the detector also moves, so that they always are on the same Rollin circle. So usually when designing these analyzing crystals, there are two types of designs that are more commonly used. One is what is called as a Johann geometry, where this analyzing crystal is bent to a radius of 2r, and therefore, so you see here, this is the analyzing crystal, it is bent to the radius 2r, and the electron beam falls onto the specimens, and the X-rays are diffracted by this crystal, and they are collected at the detector. The difference which another geometry brings, which is known as Johansen geometry, here not only the analyzing crystal is bent to the radius 2r, but it is also ground to the radius r. So you can see it is almost like, it is sticking completely on the circle, and therefore the X-rays that are diffracted from these crystal, they converge at one point at the detector. So here the diffracted beam, all the diffracted beams get converged at a point which lies on the Rowland circle. So this has been seen to give better detection and a better yield. Then a word about the detectors. Usually the gas flow detectors are used where the gas, that is, there is a gas which is present in a setup like this, and the X-rays which impinge here, they ionize this gas, and then the ions basically causes a current in this anode wire, and this signal is detected. So depending upon the X-rays, the energy, the wavelength, the ionization is different, and therefore the current that is generated is different. So that's how the signals are analyzed. And this is just a schematic. So for example, argon is a gas which is typically used in the detectors when X-ray impinges one argon ion or argon atom. It creates Ar plus ions. It again leads to basically several secondary electrons, and therefore the current is produced. While analyzing the signal, it is also important to make the necessary corrections. These are the metric corrections which are commonly made in any electron microscopic technique, basically which are called as ZAF. So Z stands for the atomic number. So basically the atomic number of the matrix, its effect on the primary electron beam. So if the atomic number is high, what can happen is a lot of backscattering of the primary ion beam can happen. So instead of knocking out the electrons, the beam may get scattered back, and therefore then it will yield the it will lower the yield of the X-rays that come out. So basically then you will so the yield is lower. And second is the A, which is the absorption of X-rays by the matrix, if so which is typically dependent upon the mu by rho, where this is the mass absorption coefficient. So if the absorption of X-rays is high, again X-rays will tend to be absorbed more rather than ejecting the electrons or the X-ray photons out of the sample. So again therefore this correction also has to be taken into account. And then F is the fluorescence of X-rays by other atoms in the matrix that can also influence the signal. So here are some examples of the analyzing crystals. Lithium fluoride, this is penta-erythritol, then you have TAP1011, then LSM060. Their 2D spacings are also mentioned here. The wavelength that can be detected is also given, and what are the X-ray lines which are most suitably detected using these several crystals. Typically in any EPMA equipment, you don't have only one analyzing crystal. You have several analyzing crystals that are placed in order to detect, in order to improve the detection time. And in fact, nowadays there are different channels in which in each channel there may be multiple analyzing crystals that are placed, so that the rate of acquisition of data can be significantly improved. So one most important advantage of the WDS is the resolution. So basically in the case of EDS, there are certain elements which cannot be resolved very effectively. For example, here is a schematic of gold, platinum, niobium. When it is detected through EDS, it basically gives you one peak, one broad peak like this. But when it is detected in a WDS, it can very nicely separate out the corresponding peaks. So here the wavelength is analyzed, therefore the detection resolution is much improved rather than the when the energy is analyzed. Then here I have also summarized a little bit the advantages of WDS and EDS. So WDS offers high spectral resolution, and it is good for majors and tracers. Detection up to beryllium is in principle possible. It has a high peak to background ratio, so the background noise is very less, and it has a lesser dead time. Some of the limitations are that the slower rate of data acquisition, as I told, that because the wavelength is analyzed by one by a crystal, so it takes time, the data acquisition takes time. This the modern EPMA instruments make up by placing several crystals and then also multiple channels for the detection. This is has more moving mechanical parts, so sometimes the maintenance is slightly more frequent. It is much more expensive, so the initial cost is pretty high than a EDS detector. So that is with that we'll end today's lecture. And in the next class, we will look at some more methods which are based on the mechanical spectroscopy, the nuclear and the electrical methods. So, thank you.